Welcome back to Compiler Construction. In today's lecture, we'll start with our series of lectures talking about optimizations. So today we'll give an overview and an introduction what optimizations in compilers are all about. So first we're going to define what we think about when we talk about optimizations, the objectives of optimizations, and where in the compiler tool flow optimizations are located. Then we, of course, need to figure out how to evaluate if an optimization we're going to apply is actually useful. So we're talking about obtaining and applying criteria for the evaluation. We'll also talk about optimization objectives in general. So if you want to optimize, for example, for the common case or for the worst case, depending on your application. And finally, we'll look at some optimization properties. So what do we actually mean when we talk about an optimizing compiler? Now, if we take a look at optimization from the point of view of mathematics, we know that mathematical optimization means that we try to select the best element from a set of available alternatives, and this best is related to some criteria we're going to apply to the selection of these criteria. Now, with software, it's often hard to find a real optimum. So compiler optimizations, though we still continue to call them so, try to minimize or maybe maximize some attributes of an executable program. Now, problematic with this is that there is a very large search space. So this makes finding the real optimum impossible in many cases because it would just take too much time or effort. In general, optimization is undecidable and very often an empty, complete problem. So, of course, nothing we want our compiler to solve every time we run our compilation process. So we're trying for a as good as possible approach instead of a provable optimal approach in many cases. But nevertheless, we will continue just to say optimizations for the sake of simplicity here. So why do we need optimization? Now, we want to support the programmer. So programmers should try to at least write modular, clean, high-level programs that should be portable, that should be supportable. So essentially, if you look at their program half a year later, you shouldn't really spend days and days trying to figure out what it was doing. And our compiler, on the other hand, generates efficient, high-performance assembler. So programmers don't write optimal code. What this means is that high-level languages very often make avoiding redundant computations in our code inconvenient or even impossible. So for example, if we write something like this, so we generate an assignment of an array A with 2 dimensions I and j, and we add this to 1. So if we translated this naively, this would include loading or calculating the address for the row that's indicated by I, and then for the element in that row indicated by j, dereferencing that memory, then adding 1 to that intermediate value, and then calculating the offsets again here, calculating the address again, and then storing it again, which of course can be simplified quite a bit. We also want architectural independence. So optimal code depends on features that are not expressed to the programmer by the programming language because it's on a different level of abstraction. But on the other hand, modern computer architectures actually assume there's an optimizing compiler helping the processor to be as efficient as possible. So, for example, there was an architecture called Itanium by Intel, which assumed that most of the performance problems showing up with early compiled code would be solved by a number of years of compiler optimization. This didn't really work out, so the Itanium was discontinued last year, and we are still stuck with old x86 machines. So what's important is, of course, that our compiler has to ensure the safety of optimizations. So optimizations are not allowed to change the meaning of a program, obviously, so the semantics of a program. So we need safe optimizations in order to make sure that our programmer actually can rely on the optimizations to work. So when we translate code directly from a simple abstract syntax tree plus a transformation to intermediate representation to machine code, this can often be quite inefficient, as we've already seen in our previous lecture. So when we try to translate this piece of code here, so it's a function foo taking an integer parameter w, returning an integer, and doing some arithmetic operations, we can actually instruct our compiler like GCC to apply different levels of optimization. So this is done using the -O parameter to GCC. So when we pass -O0, we instruct the compiler to actually execute no optimizations, whereas when we use -O3, it can apply quite a number of optimizations. So the first thing you see, the length of the generated assembly code differs quite a bit. So what is it doing here? So essentially with -O0, it applies almost no optimizations. If we take a closer look at the code, we'll see actually there's some bit of optimization. So the first thing that happens here is after setting up our stack correctly, our stack frame, that our first and only parameter w is stored in a local stack variable here. So edi is moved to -20 of RBP. And then the next thing is we move a constant 8 into 4 of RBP. So 4 minus 4 of RBP is where variable x is stored. And we see the first instruction here is x equals 3 plus 5. So even if we instructed our compiler not to apply any optimizations, our compiler nevertheless applied an optimization here and figured out that 3 plus 5 is 8. And so it initializes our variable x immediately to the value 8, even if we told it not to. So, well, then we have a bit more unoptimized code. So we store this here in this stack location, in the stack frame location for the variable x. And so the next thing we do is we have to load it again from this location into EAX to apply the next arithmetic operation here, which calculates x times w and writes it into y. So we've just seen that w is the parameter we just stored in -20 of RBP. So we multiply the value of w, we load it from memory here, with our intermediate value EAX, we just load it from the stack location for x. And then again, we store this intermediate value now into the stack location for y, which is RBP -8. Finally, we need to calculate y -0. So what we do here is we load y again from the stack into EAX. But what we do now is, well, obviously our compiler applied another optimization without telling us. So it just optimized away -0, so it doesn't subtract 0, but just have omitted this instruction here. So it immediately stores this into z. So z is at RBP -12. So this value we just loaded into EAX is now copied into the value of z. And finally, we load the value of z again to calculate our last arithmetic expression, which is z times 4. So we load this here, copy this into EAX again, though it was still in EAX from the line before, of course. And then we have another optimization. So for a multiplication by 4, we see that the compiler actually doesn't emit a multiplication instruction here, as it did up here, because down here we're multiplying with a constant, and this is a power of 2. So for integer numbers, multiplying by 4 is identical to a logical shift of the number by 2 bits to the left. So again, another optimization here, z times 4 is just replaced by a left shift of $2. And this result is already in EAX, so this is returned, so we don't have to do an expensive copy of registers over to EAX again, and so we can just pop our base pointer again and return. So even though we told our compiler not to apply optimization, we've seen 3 optimizations already applied. So it calculates 3 plus 5, it omitted subtracting -0, and it replaced the multiplication of an integer by 4 by a left shift of 2 positions here. But, well, there's a number of optimization opportunities, obviously. So essentially, this line reads y equals 8 times w. Since we just assign y -0 to z, we can say z equals 8 times w. And then we can say we have z, which is 8 times w times 4, which is 32 times w. And that's exactly what happens when we use this O3 optimization level. So the first instruction here just copies our parameter w stored in EDI into our EAX register, and then just shifts this register 5 bits to the left, so it combines the operation 8 times and 4 times into 32 times, and that is a shift of 2 to the power of 5 or 32. A multiplication of 32. And then our final result is already in EAX and it returns. And as you can easily see, this minus O0 function obviously takes a lot longer to execute, especially since we also have a multiplication instruction here, than just moving a value and shifting it over and then returning. And our compiler even figured out that we are not doing any changes to our base pointer here because we're not accessing any variables on the stack, so we got away from all these expensive memory accesses and just work on registers here. So this is really, really fast compared to the unoptimized version. So which optimizations in general can a compiler try to achieve? So we achieved here a reduction in code size, obviously. So we use fewer bytes. This is not really relevant for PCs or server nowadays because we have gigabytes of memory, but for small embedded systems where you have flash memories in the size of several kilobytes, this can be very important because if you are able to reduce your flash size, this decides if you can actually fit your program onto your microcontroller or you can't, which would make your application impossible. And the second and maybe more important objective here is we also reduce the runtime of our program because we execute very few instructions with -0 compared to the number of instructions with -0, and these instructions are even more simple, so we don't do any expensive memory accesses, we only do some register operations. And especially for embedded systems, some other objectives are important, but these might also be important, for example, for high-performance computing, so to reduce the power consumption in watt or the energy consumption over time, measured in joule or watt hours. And these objectives, which are other than runtime, are very often, as I said, relevant in embedded systems contexts, where you actually need them in order to make feasible working products. And we call all these objectives also non-functional properties because they do not change the semantics of code, but only the properties that influence its execution. And to apply these optimizations, in general, we split this process of optimizing code into 2 stages. The first stage is an analysis. So in this stage, we're trying to find code that's unoptimized. So we find optimization opportunities. And then for all these places where we found optimization opportunities, we then try to figure out which transformation can be used to achieve whatever objective we want to achieve here, like reduction in runtime or reduction in energy consumption. So this is actually changing our code without obviously changing the semantics. So nevertheless, for what are we going to optimize? So most compilers optimize for the common case. So we know that, the application profiles might differ. And since you compile a program, maybe for a large number of different users, you do not know which application profile these users will actually apply later on. So which exact computer they will be running it on, with which input data they will be running it. So essentially, you try to somehow optimize for whatever you assume to be an average use case. Now, some applications, however, require to optimize for the worst case. Especially in real-time embedded systems, the worst-case execution time is a very important factor because it determines if a system can actually operate safely under given real-time constraints. So if it has to react to an input after a given time, and if it reacts too late, something catastrophic may happen, or if it's infeasible. And to do this, you do something like a worst-case execution analysis. So essentially, depending on input parameters and other hardware parameters, you can have different runtimes of a program. So for example, you can have a best case execution time, which would be the minimal execution time. And then you have this distribution here. And then finally, you can have a worst case execution time, which is the longest execution time that your program will in reality actually have. And this is here our black bars. And this is important because when you have a more complex program, your input space gets so complex that you can't do it with measurements alone. So for example, the light colored curve here would be the measured execution times of your program. But you see that there are some corner cases in which the worst case execution time is much higher than your measured execution time. So if you decide your system to be only as fast to ensure that the largest measured execution time for whatever 1000 experiments would be able to adhere to, but not the worst case execution time that might really occur, even though it's some strange combination of parameters maybe that leads to this, then your application is unsafe to use. And that's a big difference between what industry does in embedded systems nowadays. They very often still rely on measurements instead of formal analysis like worst case execution analysis. And that's a dangerous thing to do, obviously. Now the problem is that you need information about these numbers. So what you do in essence, you need to configure an estimate that's safe. So you need to find a number for this worst case execution time. You can usually not find an exact one because this space is far too big to explore. Otherwise you could do it with experiments, right? And this upper timing bound, you assume your estimated worst case execution time has to be at least as large or larger than the real worst case execution time of your program. But of course it should not be significantly larger, so it should have a tight bound here in order not to waste too much hardware, performance or energy on keeping your worst case execution time. So if you want to actually enable your software to perform better under worst case execution time constraints, then you would not consider the average case, which might lie somewhere here. This doesn't help you because you need to ensure that your worst case execution time maybe goes down. So you need to really optimize for the worst case instead of the common case. And a good example for this is airbag controls in a car. So this reacts, for example, to you as a driver hitting the brake pedal and then measuring the road conditions using sensors in the wheels of your car. And then essentially after you took a sensor reading, you only have a couple of maybe 100 milliseconds to react to control the brakes on each wheel in order to avoid an accident in case there's a dangerous situation on the road. And if for some strange situation of like sensor readings or stuff like that, your software might take 10 times the amount of time, then you maybe hit the tree already. And that's, of course, obviously what you want to avoid. So optimizations can have different approaches. Very often, of course, for PC style desktop applications, we use this average case. But for especially embedded real-time applications, we need to consider this worst case scenario here. Now, optimizations have become more and more difficult over the last decades. And this is because the hardware underlying our computers has also become more difficult and more complex. So a compiler optimizer programming has many architectural issues to think about. So on the one hand, we have parallelism. We have parallelism inside of a CPU, of a single CPU core, like vector units, for example. We have parallelism outside of that CPU core. We can have multi-cores, and we can also have for example, additional accelerators like GPUs or FPGAs, we also want to include in executing our program. So we need to be able to exploit this parallelism on the instruction level, on the thread level, on multi-core level, and even using completely different architectures in one project, so a very heterogeneous system using accelerators. We also need to make efficient use of the memory hierarchy. So modern computer memories not only consist of main memories and CPU registers, but because the difference of speed between CPU registers, which are usually accessible within one CPU clock, and the main memory, this difference is growing larger and larger. So main memory is not getting faster as fast as CPUs are getting faster. So essentially for each memory access, the CPU would have to wait longer and longer for main memory with each new CPU generation. And to avoid this, computer architecture designers have introduced levels of cache. So L1, L3, maybe level 3, L2, maybe level 3 cache here. And this means that software that wants to efficiently use this cache hierarchy actually has to be aware about cache management, about cache replacements, and so on. And finally, we might have energy modes, we might have heterogeneous multi-cores in our system. So we have processors applying dynamic voltage frequency scaling to conserve energy. We have clock gating, turning off parts of our processor completely. And we might have big little architectures which still have the same instruction set, but we have very slow, energy efficient cores, and we have fast and relatively energy hungry cores. And small architectural changes can have big impact on the optimizations. That makes it very hard to reason about what's actually going on. So one example would be that you have a program optimized for a certain CPU. So just one model of CPU. And this model of CPU uses a random cache replacement algorithm. Now you want to upgrade your computer to the next model of CPU, and the CPU designer decided to actually change the replacement algorithm of your cache to LRU, least recently used. So the question would be, for you as a programmer, what do you have to change? This is very difficult to figure out, so this is something better left to the compiler. So the designer of compiler optimizations would have to figure out what can we change, which optimizations can we apply to exploit LRU instead of random cache replacement now to make our program, for example, execute faster. So where are optimizations applied in our compiler toolchain? You've all seen this diagram a number of times before, and the last time we were here generating intermediate representations, and this intermediate representation level has especially been introduced to make it easier to write machine-independent optimizations. So essentially, after we generated some relatively unoptimal version of IR, we can then run through a large number of different optimizations in different orders, for example, to make our code more optimal. Well, and this still generates intermediate representation code, so that's an error on the slide here. And then we can finally generate machine code out of our intermediate representation code. We could still apply processor machine-specific optimizations here as a final step before we finally execute, emit our binary program that we can compile and link and execute. So many of these analysis and transformations, as we'll see, are general, so they don't depend on the target machine, but only on properties of the program. So we can easily apply them on the intermediate representation levels, but some analysis and optimizations are better left until after we generated real machine code, so we can do some specific optimizations on that level too. So how does a compiler actually know that a transformation leads to some optimized behavior? So let's say to some improved behavior, because we know it's not optimal. The simple approach that was used for many, many years is let's just hope for the best. So for example, we would just assume naively that a number of instructions that was reduced, so a lower number of instructions, will result in faster code. Now in general, this is true. But of course, if you replace a number of simple instructions with a very complex instruction, this very complex instruction may take a long time to execute. And there's examples for this. So on the very early CISC architecture, the digital VEX architecture, there was an instruction that actually managed to calculate polynomials, which is interesting because you would usually assume writing a whole program for this. But this machine had a machine instruction for this. And this machine instruction was used by programmers on assembly level. It was already difficult to use from like a high-level language. And then one very clever programmer found out that he could actually write a sequence of primitive simple assembly statements for solving the same problem, and that this would actually execute faster on the VEX. So essentially it would mean you have more instructions, which would nevertheless be executed faster because the hardware implementation of some feature was actually inefficient. Nevertheless, in the general case, this let's hope for the best approach has worked surprisingly well for early architectures, but not so much for what we have nowadays. So nowadays, since this optimization problem is so large, we can't solve it well perfectly to get the optimal result. What we usually do is apply heuristics. So heuristics are used in many of these optimization decisions when we don't have concrete data or concrete models, or the search space is too large. So heuristics are, for example, used for decisions taken on when to inline a function, so when to copy the code of the function to its call site, or all of its call sites, when deciding when to unroll loops, so to copy the body of a loop multiple times to reduce the loop overhead, to optimize for SIMD vector instructions, which instructions should be selected on machine level for a certain instruction sequence, which registers should be allocated to which variables here, which instructions should be scheduled when, and finally, how to apply software pipelining. So these are a number of important optimizations, and all these have to rely on heuristics, because otherwise we would wait for days and days for a compiler to produce any useful result. So what these optimizations do is essentially you compile, you run, you measure, you change options, and maybe then you repeat the whole process again. So you have your program source code, you run it through an optimizing compiler to generate an executable program, and then you run it either on your hardware. Well, if it doesn't run, that's an error, obviously, then you have to debug it. But if it runs, then you try to measure it. You can measure it on real hardware, or you can use a hardware simulator that has models for whatever non-functional properties you're interested in. So you can measure the runtime, you can measure the energy consumption, you can measure the temperature of your system, for example. And then you figure out, okay, what improvement has been achieved here. And these improvements then can be added to your configuration space. So for example, you can use genetic algorithms, you can use neural networks, or just a simple database, for example, that has cases from different compilations of different programs here, so a large database, to decide actually what to change in your compiler process. And this compiler process, as we've seen, can be influenced by switches like this O0 and O3 switch. So accordingly, the results of analyzing whatever our previous optimization switches achieved in terms of our non-functional parameters are put into a system which makes a decision to change some of the flags around, and then you can compile it again, your code, in your optimizing compiler, execute it again, measure it again, until you're sick of it, or you reach a deadline that you have to deliver your program. So that's, of course, an interesting way, because you not only have this traditional tool chain from source code to hardware, but now you have this feedback loop that evaluates the non-functional properties, measures these, tries to find some more optimal ways for your program to execute, instructs the compiler by setting these flags what to do for our next compilation, and then goes over this all again. So what you can also do is, if you have models of non-functional parameters, so you have models, for example, about instruction runtime of certain machine instructions, or energy consumption or power consumption of certain machine instructions, you can actually try to integrate models of these non-functional parameters directly into your optimization process. So what you do for this is you define a number of benchmarks for typical situations, which you obviously compile and then execute on either your real machine or your simulator. And then you measure the properties here, and you put these into a model here. For example, this would be an energy consumption model for different parameters, for example, of a multiplication instruction. So one parameter on the left-hand side, one on the right-hand side. And your model then just shows you, for example, how much energy this instruction given two parameters would use. So blue would indicate a low amount of energy, where red would indicate a high amount of energy. And then you can actually control optimizations, single optimizations that apply, for example, to select a different instruction. So to select some sort of shift instead of a multiplication, or, for example, to maybe change some order of code around. And using this model, then actually you can inside of your optimization process already apply this model instead of doing it in the feedback loop, and then generate an optimized executable program in one step without getting any feedback, and then you run it on the hardware, and then you're hopefully happy. So let's look at one example optimization we've already seen in action, and this is constant folding. So the idea of constant folding is, if the operands of an arithmetic expression are already known at compile time, then we can actually perform this operation statically. So statically always means, in terms of compiler, we do it during compilation instead of during runtime. And so this means we only have to do it once while we're compiling the program, and not a million times when we execute the program. So some very simple examples here are this expression here. So int x equals 2 plus 3 in brackets times y. And of course we know we can add 2 plus 3 together to 5. So this value of this expression will never change during the runtime of our program, so our compiler can immediately replace 2 plus 3 by the value 5 and use this for multiplication. Or a logic expression b and false is always false if b would be a Boolean variable here. So the question is, what performance metric does constant folding improve? And this question is in general actually undecidable. So we don't really know whether an optimization actually improves, for example, performance. But one question that we can actually decide is at which compilation step we should apply this optimization. And we can apply this obviously on the intermediate representation, because this expression is not dependent on any target architecture specific feature. So we could, for example, apply it after the optimizations that have already ensured that all the constant expressions that are constant have been generated as constants, and so now you can fold all your constants that you achieve together to make your program even more optimal. So the question is, of course, we need to ensure that our semantics doesn't change. So we need to ask ourselves when we design such an optimization, when is such an optimization actually safely applicable? So when is constant folding safely applicable? Well, for Boolean values, yes, always, that's simple. For integer values, almost always, yes. So here's already an exception. This is an exception which is probably obvious. It's a division by 0. So this is a case where we cannot allow our computer to continue an execution. And this is usually detected by executing the division instruction. So if we replace this by something else, then we wouldn't get a runtime error when our program decided to divide by 0. So usually a compiler can figure this out and just refuse to compile your program. Now for floating point values, you need to apply caution, because depending, for example, on the order of floating point operations, rounding effects may lead to numerically different results, especially between your compiler platform and your execution platform. For example, when you do cross-compilation from one CPU architecture, but you compile code for another one. So in general, you have to consider safety, but this really depends on your language semantic, whether an optimization is safe or not. And in general, languages that provide weaker guarantees to the programmer permit more optimizations, but in turn they have more ambiguity in their behavior. So if you're interested in this is a very complex topic. We gave you literature reference here to learn a bit more about. So in addition, we can do more things that are very similar to our constant folding. So the more complex thing is algebraic simplification, which is just a more general form of constant folding. So this makes use of mathematically sound simplification rules. So for example, identities. So we know that a times 1 is a, that a plus 0 is always also a, or b or false is also b in any case. And you can also use some a bit more advanced rules like associativity and commutativity rules. So we know that a plus b executed first and added c in general is the same as first adding b plus c and then adding a. This is true for integers mostly, but not for floating point values, so you need to be careful here. The same applies to commutativity, so adding b to a should be the same as adding a to b, and usually for integers it's safe to assume that is the case. So you can combine algebraic simplification with constant folding here. So you can, for example, have this expression here, a plus 1 executed first plus 2. And if you apply as associativity, you can change the brackets to first calculate 1 plus 2, and then add a later on. And of course, then you can do constant folding here and add 1 plus 2 to give the result 3. So finally, you would just add a plus 3, so you would save one addition here. Or you could calculate 2 plus a plus 4. And then first you can apply commutativity here. So 2 plus a is a plus 2. And then you can apply associativity here to first add 2 plus 4, which can then be folded into our constant 6. So you would again save an addition here. Now, you see that this second example already applied two different optimizations, so an algebraic simplification and constant folding here. And we applied these in different orders here. So essentially the question is, it's obviously obvious to iterate these optimizations until we can't find any optimizations anymore to apply. The question is how many iterations should we actually allow, and in which order should these optimizations be applied? Well, another optimization that's interesting is what we call strength reduction. So strength reduction replaces an expensive operation with a cheaper one. So we've already seen an example for this in our first example for code generation with the different optimization levels. So we've seen that a times 4 for an integer variable can be replaced by a left shift of a by 2 positions. We can actually apply this also to non-powers of 2 as a multiplication factor here. So for example, our compiler would know that a times 7 is a times 8 minus a, and a times 8 again is a power of 2, so this is a left shift 3. So a left shift 3 minus a is probably still faster to execute than a times 7. And we can also do this for divisions, which are even more expensive than multiplications in the common case. So a divided by 64 is a left shift by 6. Division by non-power of 2 complex constants is more complex for integer numbers. If you're interested in this, there's great advice in literature reference number 8. Now, if this strength reduction is actually effective, so if it actually does optimize your code, or if it doesn't make it faster or even slower, depends on the architecture. So especially this replacement here of multiplication and division by a shifter, this is only useful if a fast shifter is available, a so-called barrel shifter that actually can do a shift of a value by something between 1 and 32 positions in one clock cycle. And this is a difference. For example, if you have one of these very tiny ARM cores for microcontrollers and Cortex M0 core, you can actually apply two different multipliers when you design the hardware. So essentially, the multiplier in one machine may take only one cycle, whereas the multiplier in the smaller configuration is slower and takes 16 cycles to multiply. So essentially, for replacing a 16-cycle multiplication by a shift, this would be a useful approach, whereas replacing a one-cycle multiplication by a shift and a subtraction here, for example, would maybe even result in slower code here. So for our x86 assembly, for example, we need to figure out what's coming out here. So if we compile this code here, that actually calculates z equals a times 7. If we compile it with -0 here, in this case with our Clang compiler, then it generates an IMUL instruction, so an integer multiplication of our constant 7 with our value z, which is at RBP -4, and stores it in EDI. Whereas when we use the optimization here, then it app uses actually this relative addressing mode by loading the address of RDA times 8 into EIX and then subtract it once. So a times 8 using a shift minus z. So the code coming out of the optimization may sometimes be difficult to understand and difficult to figure out what's really going on. So this was a quick introduction into optimizations, but we'll go into optimizations in quite a bit of a detail because the back end gets more and more relevant for compilers compared to the front end, because all these optimizations are really necessary to be able to exploit your modern computer architecture. So in our upcoming couple of lectures, we'll talk in details about the different analysis and transformations we can apply to our intermediate representation code to generate more optimal code. And here's a number of references. So some of our previous research at Dortmund, for example, the influence of the register file on the energy consumption, code size and execution time of code. So this would be optimization very close to the machine. Different ways to orchestrate different compiler switches, compiler optimization switches for automatic performance tuning. Then we have a machine learning approach to actually find optimal optimization sequences. We have power analysis of embedded systems. and also energy models from my previous work group here. And then we can do static analysis of energy consumption, for example, by Neville Grech's PhD thesis. And finally, there's an interesting article about optimization safe systems, so what all this undefined behavior that we might have might lead to. And finally, a very nice thing to read is Hacker's Delight, which has all sorts of binary and number tricks that you can actually use to optimize your code. So that's all for today. Thanks for listening, and until next time, bye.